Oh, goodness.
Okay, it's just about time to start now. Well, I guess I should turn this on. For those of you on Zoom, I'm still getting a few things ready here, so we'll start in just a moment. Okay, I will probably take roll a little later on in the class just to make sure, but several more people have unfortunately had to at least temporarily leave the classroom, so we'll hope that trend doesn't continue. But I'll take a look and see who's here maybe in another 5 minutes or so. Anybody have any questions, concerns, comments they'd like to raise before we begin? And I will say, for those of you on Zoom, first of all, jump right in if you have a question or comment. Unfortunately, today, once again, the room speakers aren't working, but I've got the volume cranked up to maximum on the monitor here, and so hopefully we will all be able to hear what you're saying, even though it's not coming through the room speakers. Okay. Eva, if you're there, can you speak to make sure that you can hear me and I can hear you?
I can hear you perfectly.
Great. Thank you so much.
And there's somebody that will be joining us. Oh, he's already here. Never mind. I'll stop now.
Okay. Great. Okay, well, so we're really getting into the thick of it now, and I hope you're finding the reading entertaining and somewhat, it should seem confusing at this point because statements are being made that directly contradict our intuition about the world, the intuition that we sort of grew up with. What I'm claiming is sort of similar to a Newtonian intuition. And all of this should be, at least technically clarified kind of by the end of chapter 7 by exactly what the confusing statements that Merman is making in this chapter They'll be addressed by the end of chapter 7, but he's just raising the questions now about what assumptions we're making, and it's not exactly clear how questioning those assumptions is going to help us see that the speed of light can be the same no matter who's looking at it, even though it appears contradictory. So today, just to finish up with some things, there were, I think I stopped in the middle of some reading response questions on chapter 2, and I thought I'd try to continue just with the ones that I had placed into the slides presentation here. So let's look at these. What makes light, and by extension, the value of C, so special? Well, I guess one could say that nobody really knows what makes the particular value of the speed of light what it is. Of course, it has different values in different units, but that particular speed, there's no good answer to that. It's something that's experimentally determined. Now, what makes light so special? Well, light happens to, when we think of it at least as a particle, we think of it as a massless particle, and only massless particles can actually travel exactly at the speed c and at no other speed. Particles like electrons and protons and neutrons that have a mass can travel very close to c, but they can also travel at much slower speeds. And so, light is somewhat special in that sense. It's not the only particle that's like that. There are other massless particles, and those particles also travel only at the speed c. But we only are going to see these very interesting relativistic effects when something is moving at speeds close to c, and light has no choice about it, so it's just the easiest thing to sort of probe these strange effects. And the first manifestation we're seeing of that is the fact that it moves at the same speed no matter who is observing it, and that seems contradictory. Second one, so if I'm understanding this correctly, that means that an observer could be traveling at 99.99% the speed of light, and should a beam of light shoot by this observer, the relative speed of light would be c. Yes. Even more probably ridiculous sounding is if that person is, you're sitting here in the room, someone travels by at 99.99% of the speed of light, they turn on a flashlight, you're going to see the light from that flashlight go almost at the same speed as them, because it's got to be moving at the speed of light relative to you, and they're, for all practical purposes, almost there, right? So you're going to see the speed of light and this person who turned on their flashlight almost moving together. The light's going to move ahead of it ever so slowly compared to you here in the room. But if we ask the person after the fact what they observed and what they measured, they would say, oh, I measured that beam of light moving away from me as I was zooming across the room here at the speed of light at 3 × 10⁸ meters per second. And that seems contradictory. One way to answer this question, how can it exist at 2 speeds at once, is to say, well, a speed isn't necessarily a fundamental property of something, right? I don't have a speed. A speed is something that is observed by someone who's in a particular, say, inertial reference frame. That's one way to get a speed, right? So an object that's out there floating in space doesn't have a speed, but if someone observes it, they will observe one speed. So there can be different speeds that different people observe. The strange thing here is that they're all arriving at the same speed when we're talking about light. This is, I think, the same question right here, and it's sort of a related question. So one observer is traveling at 99.99% of the speed of light and observes the light as traveling at c. Another observer who is at rest relative to the other observer still observes the same light traveling at c. That seems to suggest some extremely special properties of light. Well, not necessarily things that are special about light, but things that are special about any object that is traveling relative to the person who's observing it at a speed that's close to the speed of light. So there's nothing inherently special about light. It's the only thing that's special about it is that it can't help but travel really fast because it's massless. Other massive things can almost travel as fast, and you're going to see exactly the same effects for those objects. So, for example, it's not just light, but for example, if someone's zooming by here at 99.99% of the speed of light, and they shoot a physical particle ahead of them from their point of view, right? They're in some rocket ship going by us. They shoot a physical particle ahead of them at 99.99% of the speed of light. They will see it, of course, going at nearly the speed of light. But when we measure it here in the room, we will also see it moving at very close to the speed of light. So there's nothing special about light in that sense. All particles, all things, even us, spaceships and all things, behave the same way when they're moving at close to the speed of light compared to the person who's observing it. Seems to imply a logical contradiction. Yes, it does, and that's sort of where we're stuck right now, and the next 3 chapters are going to kind of undo that. Proposition 1, observer 1 is traveling at 0.5 c. Observer 2 is at rest relative to observer 1. Well, maybe I misread this. In any case, it seems contradictory that both are saying that the speed of light is c, but we'll show in the next, I think, 4 chapters exactly how we can disentangle this. But it's going to require sort of deconstructing our whole notion of how we think about space and time. Okay, so before we go on into chapter 3, the subject for today, let me just kind of very briefly summarize what we learned in chapters 1 and 2. Chapter 1 talked about the principle of relativity. That means that there's no such thing as moving relative to space itself. If you take everything that you're doing with your experiment and move it in a certain direction at a certain speed, you'll get exactly the same result for your experiments as long as it's moving uniformly. So there's no sense in which one can be moving relative to space itself. The only motion is relative to other objects. Chapter 2 was about the more confusing principle of the constancy of the speed of light, and that we're going to have to disentangle. But the idea is going forward, we're going to start with those 2 principles and see what we can derive from them. In other words, let's just hang on to those 2 principles and take them as absolutely true and see what follows from it about what has to be true about how time is measured, how lengths and distances are measured, and when compared between different inertial reference frames. So that's where we're going from here. And chapter 3, which you read last night, sort of sets up the problem. So again, I think this is Merman's terminology, but he abbreviates the principle of relativity as PR, just so that when we're referencing it, we don't have to write a long collection of words. And the same thing for PC. I guess that's supposed to be the principle of constancy of the speed of light. Will be abbreviated PC. Okay, here's in chapter 3, Merman's basic approach. And several of you wrote about this in your reading responses. We're going to try to construct a proof that the principle of the constancy of the speed of light is incorrect. In other words, we're going to derive a contradiction. And we're going to do that by having a kind of race. It's not really a race because nobody's trying to win this, but we're going to watch things moving at different speeds. So what we're going to do is have someone sitting at rest. They're in an inertial reference frame, so they feel like they're at rest. There's going to be another person, observer B, who's moving by at half the speed of light. So it's at some time t equals 0, B happens to be passing by at, and A would say they're moving by at half the speed of light. And A would also say there's a pulse of light that happens to be passing by at speed, of course, C at time t equals 0. So at time t equals 0, they're all at the same position as A. And we're going to consider the following bit of logic and try to figure out where might be the problems or hidden assumptions we're making in this proof that there's no way the principle that PC could be correct. The first claim is that light passes person A at speed c. Okay, that's what PC is claiming. The second claim is that person B, or that particular inertial reference frame that B is sitting in, moves past A at a speed c/2 in the same direction as the light. And so therefore, the claim that's being made that contradicts the principle of the constancy as the speed of light is that light must move away from B at speed c/2. In other words, looking at this picture, And based on the intuition we used on those worksheets, the first day of class, or the first day of class, I guess it was the second day of class when we discussed the first chapter, we would say, look, if someone's moving to the right 3 times 10 to the 8th meters per second divided by 2 every second, and then something passes them at going 3 times 10 to the 8th meters every second, then this is going to get half of 3 times 10 to the 8th meters ahead of B every second. That just seems logically, we can't avoid it. Well, Einstein's going to tell us exactly how we can avoid it. So let's think about how we would, Merman suggests is that we think about how we would construct a proof of this claim. And here's one way to think about the proof, you know, get the aha, gotcha kind of moment. So here's a later time t. B, this is all from the point of view of observer A. Observer A says at a later time t, B has moved a distance d ahead of A. And of course, because this pulse of light is going exactly double the speed of B, it moves twice the distance, 2d, ahead of A in that particular time. Okay? So let's consider some of the facts here. The first fact is that, according to A, the speed of B, well, how do you measure a speed? You measure a distance they moved divided by the time it took to move that distance, right? That's how we calculate a speed. In this case, the distance that was moved is what we're calling
Okay, I don't understand why, but I can't hear you anymore.
I can't hear you either.
Professor Kelly, can you hear us?
Can you hear me now?
Yes.
Yes.
Okay, there's a problem with, I thought I had fresh batteries in here, and apparently I don't. So let me try changing out my batteries. If not, I may have to use, so I'm going to go away for a second because I have to turn off my microphone. Thank you. Can you hear me now, Eva?
Yes, I can hear you.
Yes, I don't know what happened. I put fresh batteries in my wireless microphone yesterday before class, and they've already gone dead, so maybe they weren't as fresh as I thought they were.
At
Let's
least,
hope these ones do better and last for a couple of days at least.
good. At least it wasn't the connection. For a moment, I thought you were just frozen, and that's why I couldn't hear you.
No, you know, unfortunately, I get no warning when my batteries are about to go out on this particular microphone, so it just goes dead, and so I have to be, I've just ordered a set of rechargeable batteries so I don't keep throwing away non-rechargeable batteries, and they're supposed to arrive today. So that means I can have a freshly charged set every day and not have to worry about it in the future. Thank you. Okay, so I'm not sure where we were in terms of explaining this, but we're going to imagine that A and B and the pulse of light are lined up at one particular time. I'm sorry for repeating myself if you guys heard this before. And at some later time t, well, B is moving at a speed of half the speed of light to the right, whereas the pulse of light, of course, is moving at the speed of light. So according to A's measurements, B moves some distance to the right, and the pulse of light moves twice that distance to the right, as measured by A. So one way to calculate the speed of B past A, which of course is C over 2, okay? The speed of B past A, as A measures it, is going to be the distance B moves, I'm just going to call that D, divided by the time that elapsed. I'm going to call that T. Now, let's also calculate how far, according to A, that this pulse of light gets ahead of B in that particular time. And of course, the speed of the light pulse past B is, well, it moves an additional distance D, and the amount of time it took to get from being lined up from B with B, that was over here, to this point in time, is also d over t. And so those two quantities have to both equal c over 2. And so what we've concluded here is that the speed of light, the light pulse past B, seems like it's got to be c over 2. I mean, I'm saying something that we've remarked on before, so this isn't a new proof here, but I'm trying to put it into just absolutely stark terms here. Yet somehow Einstein is telling us, or Michelson and Morley through their experiment are saying, that when B measures the speed of the light pulse, B, remember B is a bob here, so that's why I'm saying he finds C. When B measures the speed of the light pulse past him, he finds C, even though it seems like, according to A, that couldn't be the case. And so the question that Merman wants to investigate here is, what are the hidden assumptions we make when we use this proof to conclude that the speed of the light pulse past B has to be half the speed of light? And here's what he says, and we're going to see exactly how this plays out. So I've just sort of shoved everything up and compressed it towards the top. Where have we gone wrong? More importantly, what are the things we're unconsciously assuming here? The first thing that's being assumed in this proof is that when observer A, or you can think of A as being in an inertial reference frame, when A measures the distance, a distance to be d, that B will also measure the distance to be d. That's true in our everyday experience, but we're not well versed in watching things move past us at close to the speed of light. And in this case, B is moving really fast and C is moving, at the speed of light. So it is true that A measures that this light pulse has gotten a distance d ahead of observer B, but there's no reason to assume, because we have no intuition about things going this fast, that B will also perceive this distance to be the same distance d that A measures. Okay? Maybe the amount of time that elapsed makes this distance, a very short amount of time, makes this distance be 10 meters for A. D might perceive that distance or measure it with meter sticks to be 8 meters or 12 meters. That sounds absurd, but there's no logical contradiction there, at least that we can see, right? Those two distances could be different, and we'll see exactly how they will be different later on. The second assumption we're making is that when we calculate what B perceives the speed of this light pulse ahead of it to be, when A measures the time interval between events to be a time t, in other words, we're taking A's view right here. A measures the time interval between this configuration and what A sees this configuration to be a certain number of, maybe it's 1 second. There's no guarantee that B measures the time interval between what's displayed in A's point of view and what's displayed on the left to be the same amount of time. It might be a shorter amount of time. For all we know, it might be a longer amount of time right now. We're making that assumption when we, derive that contradiction with the principle of the constancy of the speed of light. The third one, perhaps most concerning, or at least most unusual, is when A's clocks say that two events are simultaneous. And in this particular case, when we talk about an event, remember we use the word event to say something happens at a particular place at a particular time. So it's not only localized in space, but it's something that's localized in space and time. So here's an event. A has some meter sticks laid out ahead of A, and when B is a distance d ahead of A on the meter stick, that's a particular event. There's something that happened. Maybe B could burn a little, mark on the meter stick with a laser beam or something like that, right? That would be an event where that mark first appears. When A's clocks say that the two events are simultaneous, so here's one event. B is at distance d, and I'm sorry, I should be pointing with my mouse over here so that everybody can see what I'm pointing to. In A's reference frame, B being at this location is one event, and the light pulse being at this location is another event. And in A's point of view, those two events can occur at the same time. The claim is that there's no guarantee that B will assess the situation that these two events occur at the same time. They might occur at different times. In other words, one might happen first and one might happen later. We'll find out that in B's point of view, this one will happen first and this one will happen later. That's very confusing, but those are all assumptions that we're making when we think there's some contradiction about the speed. I should check my battery power. Still looks good, so I'm not sure what was wrong with those other batteries. But so we'll find out that Einstein's going to show exactly how all these assumptions are wrong if we're going to cling to the principle of relativity as being absolutely correct and the principle of the constancy of the speed of light being absolutely correct. These three assumptions don't follow, and in fact, they're not only do they not follow, they're not true. They're false in this case. Now, in this case here, I'm talking about things called events, and I just reminded you a little bit about the word event, but let's flesh that out a little bit because we're going to be talking about events for the rest of the semester. Okay, so here we're talking about distances between two events, right? Firecracker goes off here. Later on, a firecracker goes off over here. We could assess the distance, spatial distance between those two events and the time interval between the two events. An event is something that happens at a particular place and at a particular time. So for example, a firecracker explodes, a rocket arrives on Mars. That's something that even if you're in lots of different reference frames, you can identify that event, right? You can see, oh, there was a particular time when the rocket arrived at Mars. It wasn't there before, and it is there right at that time that it lands on the planet. A pulse of light passes the x equals 2 mark on A's meter stick. So there's a pulse of light that's passing by it. Maybe it even burns a little mark in the meter stick as it passes by. When that burning process happens, that's something that everyone in every different reference frame can identify. So, now, these are all events that everyone can sort of identify visually. We're also going to use the word event to refer to just a point in space and time. Like we might say, here I am in space. For those of you who are on Zoom, I know you can't see me because I'm not on camera now, but I'm pointing to a particular location in space at a particular time. Nothing of interest happens there, so it's a little bit ephemeral sounding, but we're also going to say, even though nothing of interest happened right at the place I pointed at that particular time, we're still going to call that location in space at that particular time an event. So locations in space and time are just going to be called events. Whether or not something of interest, public interest, happens there, we can still, in a particular reference frame, measure where an event is, even if nothing happens there, right? I could have a system of meter sticks and say, oh, right there was an event. Nothing of interest, but in my meter sticks, it was at x equals 5, y equals 2, z equals -1, and it occurred at t equals 3 seconds. According to my clocks. It depends on how I set up my meter sticks and where their origin is, but it doesn't have to be something that's publicly visible in order to talk about an event. It's also important to remember that here we're talking about an inertial reference frame, and I've been speaking as though A and B are single observers, but we're going to imagine that A has at her disposal an infinite collection of observers, we can imagine, that are stationary with respect to A and are placed all over the universe and can make local measurements. So that if we wonder where something was at a particular time, they use a local clock on the local meter stick and measure it in that coordinate system. So we're going to speak sometimes as if A and B are individual people, but we're going to use measurements made by their fellow scientists that are all sitting on their huge inertial reference frame at rest with respect to one another to make those measurements. Okay, so for example, here I'm imagining there's an event, firecracker goes off, A would use A's particular version of meter stick. So if this is where A is, maybe A's origin of their coordinate system, their XYZ coordinate system is over here. So this event might occur at some positive X value, some negative Y value, and so on. And in B's coordinate system, maybe B's origin of their coordinate system is over here. So they're not going to necessarily agree on what the XYZ coordinates are or the time coordinates. We're not going to assume that these clocks are even synchronized, and we'll find out later on there's no way to synchronize them, because when they're all synchronized in one inertial reference frame, when somebody moves by, they're all going to see the clocks going are all staggered with respect to each other, so they don't even read the same time anymore. Okay, so speaking of events, in this particular scenario here, there are 3 events of interest. The first event is that everyone's lined up at this starting line right there. That's a particular event, right? Where something, in this case, we're talking about publicly identifiable events. All 3 of these were at the same location. That's an event at A's 0 meter mark. A second event is that observer B or person B was at A's D meter mark on A's meter stick. So if we're laying out A's meter stick ahead here, B reaching point D on A's meter stick, you know, maybe it's the 1 meter mark or something like that, that's an event. And the light pulse reaching the 2 meter mark on A's meter stick is a separate event. So there are 3 different events that are kind of displayed right here, okay? And the real question that we're trying to get at, or Merman's trying to point at here, is if A measures the time interval between events 1 and 2 and 1 and 3 to be t, and that's certainly true. I know it's obscured by the top here, but I tried to scrunch everything up to the top. If the time interval between this event here and this event here, where B passes the D mark on A's meter stick, is time t, and between this event and where the pulse passes the 2 meter mark, that's also t, and A measures these 2 distances to be d, then the question is, will B measure the same times and distances between those events? And the proof in this case, I put the proof in quotation marks because we're going to find out that the proof hinges on that being true. We're going to see that they're inconsistent with the principle of relativity and the principle of the constancy of speed of light, and therefore the proof fails if we're going to accept P, C, and PR to be true. Okay, so what we're going to find out is that A and B actually measure different distances and different times between these events. Even though they're publicly identifiable events, A and B are going to disagree on the time intervals and the distances between them. Okay, I think there was one other thing I wanted to say before I go on to that. Yeah, Merman makes a point about not worrying for now how they could possibly behave differently. It seems impossible that they could be that way, but that's just because we're using our intuition about ordinary everyday objects that don't move very fast with respect to us. But rather, we're going to concentrate initially on how they have to behave if PR and PC, the principle of relativity and the principle of the constancy of the speed of light. You can see why I want to have an abbreviation for that, or what Merman does, because it's so hard to say. If we assert that those are true, these other behaviors about distances and times have to be true as well. Okay, so at this point, any questions before we go on? I feel like I'm talking a lot today, and unfortunately I don't have a worksheet to practice with this. Merman's sort of setting up the argument, and then we're going to have very detailed arguments over the next 4 chapters. And those will involve things that we can calculate with and actually find out interesting properties about. But right now, in chapter 3, everything's left kind of in a state of confusion and anticipation about how we're going to get out of this mess that we've gotten ourselves into, or that Michelson and Morley maybe have gotten us into. It's not silent. Well, it is silent, but that's on purpose here. So, okay. Here's here's a point that many people brought up in the reading responses, and that is that Merman points out the difficulties that come with the ordinary way we speak and use sentences and the assumptions that lie behind them. So we've assumed that distances and time intervals up till now in your life, measured by people in relative motion, would agree. If I have a firecracker go off here, and then a little bit later, one goes off here, and I say, oh, they were separated by 3 meters from my point of view. We all assume that if you're zooming by at 10 meters per second, you're going to measure the same distance between those events. Even though they'll be moving, you're going to measure you would measure the same length of an object, events that were happening at the same time, and also you would measure the same time interval between them. If I say they happened 2 seconds apart, you would also measure them on your clock 2 seconds apart. Now we're saying that that's not true, but it's sort of baked into our language, the way we use it. So we're going to have to be very careful to specify who made a particular measurement. And several of you raised questions associated with this. So please jump in with your own examples if you don't understand what the point is. So here, I believe this is an example straight from the book. These are what Merman would call relativistically ambiguous statements. In other words, that we're making a statement about what's true, but we're not saying who is saying it. And these are going to be statements that now depend on who's making the claim. 5 minutes after the game started, a touchdown was scored. The assumption here is that we know in the background of this conversation what game we're talking about, where it was played, and so on, right? But we say things like this all the time. 5 minutes after the game started, a touchdown was scored. The claim is that this is relativistically ambiguous. We're going to find out when I look here at property 2, the things that we're questioning the assumptions of. Property 2 down at the bottom says, if one IRF measures a time interval to be sometime t, another IRF is going to agree that the time interval between those two events is t. So we could say one event was the start of the game, the second event was the touchdown was scored, and the assumption underlying this statement is that everybody's going to agree that it's 5 minutes, so we don't have to say who said it. Now, in all likelihood, it was someone who was there at the game and not moving at a great speed. But if we're going to allow people to be moving by at close to the speed of light, watching the game as it's going on, they may disagree about how much time elapsed between the start of the game and the time the touchdown was scored. So we would have to amend this with something saying, according to a person who was at rest in the stadium or something like that. Then it would be unambiguous. The distance from Earth to Sun is, okay, you give a distance. You could look it up on the web. What's the distance from Earth to Sun? Of course, it varies a little bit from which time of year, but at a particular time, the distance from the Earth to the Sun, when it's farthest from the Sun is a certain distance. This, again, is not saying who's observing it, but it's assuming that everybody's going to measure the same distance between two objects at a particular moment in time. So right now, the distance from Earth to Sun is a certain distance for us. Is everybody going to agree with that? The claim is no. If someone's zooming by our solar system at close to the speed of light, they're going to see actually a shorter distance between Earth and Sun than we will, assuming they're moving along the direction that we're measuring that distance. Okay. Third example, the two planets were at their farthest points from Earth at the same time. We say this without thinking all the time, but it's assuming property 3 down here at the bottom, which is not going to be true. We're calling this into question. This is an assumption that's not going to be true going forward, and we'll see exactly how it has to be not true in chapter 7. So we're assuming that if two events, the planets being at their farthest point from Earth, take place at the same time in one inertial reference frame, they're going to be assessed to be occurring at the same time in another reference frame, and that's not true here. Okay. Now, Merman also brings up that just for convenience, he is going to use a certain kind of shorthand notation, even though it sounds superficially relativistically ambiguous. When we say something like, consider a stationary meter stick, it sounds like you should say, well, stationary compared to whom? But we're going to understand this to mean, consider a uniformly moving meter stick from the point of view of an inertial reference frame in which it is at rest, right? If there's a meter stick that's moving uniformly, you could always take the point of view of riding along with the meter stick, and then it's at rest, right? And so when we say consider a meter stick at rest, we're just going to assume that that is a statement that is referred to by one person who happens to be moving along with it, although other people would not see it as at rest. We'll also often refer to, if we have an object that's moving uniformly, or maybe it's at rest, that's one way to move uniformly, we'll refer to that object, A, maybe it's Alice, as A's frame, or A's rest frame, or A's IRF. They refer to, if something is moving uniformly, it could be an observer or something like that, a human being. If they're moving uniformly, we would say their frame is the frame in which they're at rest. There's a reference frame that rides along with them in that sense. Okay, questions again so far? Please ask questions, because I know that today in particular, I don't have a worksheet and I don't have voting questions to stop and help us think about these things. And it is a little bit disconcerting to have everyone spread so far apart with masks on, so I can't really see your facial expressions of any surprise or, sleepiness or anything like that. It's just sort of zero feedback. Okay. Here, so again, along the lines of these assumptions down here, here are some things we're not going to assume for the rest of the course, even though they are everyday assumptions that we would make. The length of a meter stick is the same as observed from its rest inertial reference frame as from an inertial reference frame when it's moving. So I've got a meter stick. Of course, we say a meter stick, the length of a meter stick is going to be a meter. Well, it is, by definition, always in its rest frame. That's what we mean by a meter stick, right? When we construct a meter stick, while moving by it at a speed close to c, we construct.
We lost your sound again.
Okay.
Okay, we have it.
You have it back again?
Yep. I don't know what it is, but we lost it.
I don't know what happened either. My battery's not low now, but that's strange. Maybe our connection just blipped out for a second. I hope this doesn't become a persistent problem. I was saying that we're not going to assume that if we have a meter stick, if I'm sitting here in this classroom and I have a meter stick that's, of course, 1 meter long, what that usually means is I've constructed the meter stick from the point of view of someone who's at rest, essentially, with respect to the meter stick, and I made it 1 meter long. We're not going to assume that someone who's moving by that meter stick along the direction that the meter stick is oriented would measure using their own meter sticks that are at rest in their frame, would measure my meter stick to be exactly 1 meter. We'll find out that they'll measure it to be shorter. Although when someone's moving really quickly, you have to be very careful about how you make measurements of the length of something. When we make a measurement, we always measure the two ends at the same time. So we'll have to be careful about that. Okay, the second bullet point is just a restatement of that. Moving meter sticks has the same length as meter sticks at rest. Well, a moving meter stick and a meter stick at rest, they could be the same meter stick. They're just being viewed from different inertial reference frames, right? So we're going to assume that there's nothing wrong with a meter stick. Somehow, when it starts moving, it doesn't automatically get shorter. It doesn't change its essential properties. What happens is when it starts moving it, I'm viewing it now suddenly from a reference frame in which it's moving, or I'm moving relative to the meter stick. And things can change. We didn't grow up in a situation where we have a lot of experience with measuring lengths of things that are moving at close to the speed of light past us. Similarly, we've already seen this in the light pulse clock example that we did yesterday, that moving clocks tick at the same rate as stationary clocks. What did we find out about the light clock yesterday on the worksheet? It ticks at a certain rate. Remember, we've got two mirrors having a light pulse bouncing up and down between it. We're going to call one tick the amount of time it takes, or one tick is one up-down bounce for that light pulse. Now, if I take that clock and I view it from the point of view where it's moving really rapidly with respect to me, or I'm moving very rapidly with respect to it, am I going to see that clock ticking more quickly or more slowly? Do you remember what the result of the worksheet was? More slowly. Okay, so sometimes we'll just summarize that by saying moving clocks run more slowly, or moving clocks run slow. That doesn't mean there's something wrong with the clock. The clock is still behaving exactly as it should, and there's nothing incorrect about its behavior. If you sit at rest with respect to that clock, it's ticking the way it always should, so it's a perfectly well-functioning clock. But when it moves by me at a certain speed, or if I move by it at a speed close to the speed of light, I am going to see it ticking more slowly as measured by comparison with my clocks that I have in my own reference frame. And that's not just true for that light clock that we constructed. You might say, well, that's a broken, why would you make a clock out of a beam of light? We know beams of light behave really strangely. But it's going to be the same for any clock, like the clock on the wall, the clock on your wrist or on your phone. Your heartbeat is a kind of clock, right? It has a regular tick time, and those clocks are all going to be going slowly. So when someone moves by you at close to the speed of light, even though in their own rest frame they feel completely normal, when you watch the beats of their heart and make measurements of them, you're going to find it takes a longer time between the beats of their heart. And that means when you watch them, it's hard for one person to watch them because they move so fast past. But if you make measurements with all the people in your inertial reference frame of just what's going on as they pass by the local observer after as time goes on, you would find after looking at the data that their heart is beating slowly, and everything they do is slowed down. Their thinking is slowed down, they age more slowly, and so on, because those ticks take longer. Nothing feels different to them in their own reference frame. Furthermore, two inertial reference frames agree on where and when something happens. I mean, I guess it's hard to interpret what this means, because if something happens in the middle of just empty, dark space, far from anything, something happens. Suddenly a firecracker goes off, and then it disappears. It's hard to say what it means to say exactly where and when that occurred, because there's kind of no reference points. But what I can do is say, in my inertial reference frame, I have a bunch of meter sticks extending out very long distances in the X, Y, and Z directions in 3 different directions. So I've got a grid on which I can measure coordinates. And I've got a bunch of clocks everywhere, and I've carefully synchronized those clocks so that they always, maybe at a certain time I have them all read 12 o'clock, and they're all behaving perfectly normally. If that firecracker goes off, I can say in my coordinate system, it was at x equals 3 meters, y equals 2 meters, x equals minus 1 meter, and it occurred at time 12:02 exactly. Well, of course, different inertial reference frames aren't going to agree on where, if that's what we mean by where and when something happens. Well, their origins aren't even lined up, right? Maybe somebody else moving, their origin of their coordinate system was at some different location, and maybe their clocks aren't even synchronized with mine, so that when mine read noon, theirs reads 2 o'clock. So it's hard to say what that one means, but I think, of course, they're going to disagree, because the only way they have to measure where and when something happens is using their coordinate systems and their clocks. Two inertial reference frames agree on what events are happening now. This is a list of things we're not going to assume. We're going to show that they are, it's not possible to assume them because they will be violated during the process of this course. Two inertial reference frames, we can't say that they're going to agree on what events are happening now. In other words, it's easy to think, I wonder, what's happening on Mars right now. Or I wonder what's happening at Alpha Centauri, on a particular planet near there. Well, for me, we're going to find out there is a sense of what's happening right now. But when I ask that question, and suppose I say, at the time I asked that question, according to my definition of now, because I've got a bunch of clocks in my inertial reference frame that are all synchronized, and one of them happens to be near Mars, when I speak those words, a little alien popped his head out of a hole in the ground or something like that, right? And those two events, we would say, were simultaneous. Right when I asked that question, an alien popped the head up and then popped back down again. If someone is moving by my inertial reference frame in a different inertial reference frame at a very high speed, they are not going to see those two events happening at the same time in a lot of situations. We'll find out exactly when that's not going to be true. Jack? Okay, I'm going to, for the benefit of the people on Zoom, I'm going to try to repeat the question step by step. So if you're building up something, ask a little bit and then pause, and I'm going to restate it for the benefit of the Zoom folks because it's hard for them to follow when a question is asked in the room. I know it's a little bit cumbersome, but that's just the world we're living in now. So if you could start over again, Jack. Okay, we put a clock on the blackboard. And I run at half the speed of light relative to the blackboard. Yes. So I run back to the blackboard after that. Yes, both on the way out. So the question was, in this situation, I'm going to see the clock running more slowly, just based on our intuition we got from the worksheet yesterday, that if you're moving relative to a clock, you're going to see that clock ticking more slowly. And it doesn't matter whether you're moving one way or the other way. So that's going to be true as you're running away from the clock and as you're running back to the clock. Okay, so continue. So the question is, if I then, after that process of running away and running back very quickly at half the speed of light or nearly the speed of light, if I sit down with the people in the room and look at the clock with them, will I see a different time on the clock? And let me ask you what you guys think. We'll poll the class. And Zoom folks, if you want to jump in, we should be able to hear you, or at least I can amplify it for the point of view, for the benefit of those in the room. Yeah. Would you see, so it's a very perceptive point that it seems like there's some problem here. I'm going to be seeing the clock running slowly the whole way out and running slowly the whole way in. And therefore, I can't have seen the same amount of time elapsed on. And yet, if I sit down in the classroom after that with the people who are in the classroom, it would be absurd if I didn't see the same time on the clock. And we're actually going to investigate exactly that phenomenon later in the book. I can't remember exactly what chapter it is, but it's past chapter 7 when we investigate that. It's related to something called the twin paradox, where you consider, maybe some of you have heard of this before, you consider someone here on Earth and a twin, so that they're exactly, at least genetically, identical. The twin gets on a spaceship, travels at close to the speed of light for a very long time, maybe as measured by the Earth person, they would say they were gone for, they went out for 10 years and then they came back for 10 years. And the person on Earth and their fellow scientists in their same inertial reference frame are watching them the whole time and seeing that their body appears to be aging more slowly because their heart's beating less quickly. All the aging process, cellular processes are running more slowly. And so when they get back, of course, they're going to see the same time on the clock on the wall, but they will actually be physically younger And it takes some subtle analysis to see exactly why that is. But I guess this is just a little teaser for what's coming on later on if you haven't heard this before. If you could travel at close to the speed of light and you traveled for, say, 2 years away, very close to the speed of light, and then turned around and came back, you would have aged quite a bit less than the corresponding people on Earth, biologically speaking. And you would have experienced psychologically less time elapsing during that time period. It's hard to imagine why that would be the case, but we have to carefully follow the logic as we go through it one step at a time. But no, in this case, yes. It's not going to happen right when it's hard to explain now because it has to do with the assessment and the asynchronicity of the clocks. So I'm going to actually put off the explanation until we get to talking about the twin paradox, because it's hard to put it in clear words without having to build it up by stages. But no, it's not that when Jack comes and all of a sudden sits down, he sees the clock tick off a bunch of time really quickly. That would also seem to be absurd too. So it has to do with the fact that, when Jack is far away, he has his compatriots who happen to be close to Earth but are in his inertial reference frame, assessing what time is on the clock here on Earth. And so we'll make that argument in great detail when we get there. But that's a good question to keep in mind. And another thing that's sort of unsatisfying, but maybe a little bit tantalizing about where we're at in the course, that there's all sorts of things that seem to not make sense right now, and they are going to be sorted out. And the hope is that all of us will understand how to sort them out by the end of the course. That's the goal of the course, to really be able to disentangle these things. But it's not so easy to just wave away some problem with a quick sentence at the beginning of the course, because we're going to have to undo a lot of assumptions that we make about when we speak about things like that. But no, it's not going to be something as simple as, we can't sit here in the classroom and see 2 different times on the wall. We already know that that never happens, and that's not going to happen in relativity either. Other questions or comments? Yeah. So the question was, when Jack is moving, I'm sorry for Jack having to be the subject of all this speculation, but when Jack was moving close to the speed of light, is he going to subjectively experience time moving more slowly? I believe that was the first of the questions. Anybody have an opinion about that? We have enough information from what we've read to answer that right now. Yeah.
Jack was for he left for like 2 years. He went for 2 years, then he was back to experience 4 years of time, even though the people back here who aren't covering the same would experience much more.
Yeah, so the claim was that Jack wouldn't feel, if I may paraphrase, that he would not feel anything subjectively, psychologically different. What would that violate in what we've read in the reading already this term? Suppose Jack could actually tell when he was moving fast by introspection, right? He just, I can feel it. Time's going more slowly now when I'm moving quickly, and therefore I can tell if I'm moving quickly or moving slowly. What would that violate in terms of what we've already read about? Right, so essentially it's the principle of relativity, what we read about in chapter 1, that there's no way to tell, there's no fundamental difference between moving and rest. So when you're moving, everything's got to be exactly the same as being at rest, if you're moving uniformly. If you're not moving uniformly, accelerating, then, well, all bets are off. But the claim is, if you're moving uniformly, you may as well be at rest. There shouldn't be any way, even psychologically or by introspection, that you can find out that you're moving. So that means Jack, when he's moving relative to Earth, people on Earth have got to feel completely normal. Jack's got to feel completely normal. But when they compare how much time has elapsed after the trip, they may disagree upon that, and that requires some explanation. Yes?
So, this might be possible to answer at this point, but if you had a camera, like a live stream setup, so we have a camera here that's connected to the camera on a ship that's going 99% of the light.
Okay, so we have I'm going to try to state this as it gets developed just so that I can remember the whole thing. We have a camera here on Earth that has a live stream from a camera that's on a ship that's traveling at a large speed compared to Earth.
Yeah.
Yes?
It's facing the clock. So we have the cameras looking at the clock on the spaceship.
Yes.
When they travel close to the speed of light, how would we see them tick at the same time? If we could look at the clock here that's ticking, just as they're traveling the speed of light, does the clocks?
Yeah, so the way we're going to, let me just try to state the end of that for the benefit of those on Zoom. The question is, how would we see the differences in the ticking rates happening if we could see simultaneously on Earth what's going on the ship? And the idea is we're not going to do that through a live stream. The problem with a live stream is it takes the information a long time to get back to Earth if it has to go a great distance. So instead of having a live stream, what we're going to do is say we have a whole team of scientists associated with us here on Earth, and they're all going to be at rest with respect to Earth. So let's imagine that we know Earth is slightly in a non-inertial reference frame, but let's imagine that we're inertial. In other words, we're moving completely uniformly. We're ever so slightly moving non-uniformly because Earth is spinning and Earth is going around the sun and the sun is moving around the galactic center and so on. But if we imagine that we were completely inertial, we could have a team of scientists that were spread all over the universe that were at rest with respect to Earth. And so instead of having a live stream, what we're going to do is, as this spaceship is going along farther and farther away from Earth, as it passes each one of our scientist observers that are at rest with respect to Earth, we're going to have them look at what the time reading is on the spaceship as it flies by. So they're only going to make a local measurement. They don't have to wait for any time for the information to travel back to Earth. And they're going to record the time that it reads on that clock in the spaceship, and they'll also record the time that it reads on their clock, which is synchronized with the ones we have back on Earth. And they're going to see a difference between those as time goes on. In other words, less ticks will have elapsed on the one that's moving. So repeat the end of the question. I mean, I feel like there was a thrust to the end of your question. So when instead of the live stream, we're actually going to have all these people recording that. And then after the recording's done, we can all come together and look at the data and compare and say, this is what happened. You know, when it was out here, it had only ticked 5 times, even though the Earth clocks, which were synchronized with the scientists all over the universe, had ticked 50 times.
There would there'd be a way to tell if I'm watching, if you could actually see it tick, and it tick on too slow.
Yeah, it's hard to, when you, so the question was, could you actually see it tick more slowly? And the problem is, if something's moving at close to the speed of light, you don't want to really, when we're saying see, we're waiting for one person to have photons arrive at their eyes from the clock. And this clock in 1 second has gone 3 times 10 to the 8th meters, roughly, sort of, farther away from us. So we're going to have to wait a certain amount of time. And that's why Einstein assumes that, you know, even though it seems ridiculously excessive, that we can imagine a set of observers who are local at every possible event, but at rest with respect to someone on Earth, if we assume Earth is an inertial system. It's very close to one place. And they're the ones who are going to take that data. And after we get back together with all those scientists, they travel for many years back to Earth, and we compare the results, and we find out that the data say that that clock was ticking slowly. It's a little bit of an abstract notion, but it avoids all the problems associated with waiting for one person, all the data to get back and fly through space to get to them. Feel free to raise that question again when we get to developing the idea of time running more slowly. That will be in chapter 5, which we'll do early next week. Okay. Here is something that raised a fair bit of comment in the reading responses, something called the principle of invariance of coincidences. and it's extremely important. We're going to use it to our advantage. You know, at the beginning of this course, it's easy to imagine that, well, almost anything goes. But just like it seems absurd for Jack to sit back down in this room and see a different time on the clock than the rest of the people in the room, that would be absurd. There are other things that it would be absurd for people to disagree on. So we're going to assume that if two objects arrive at the same place and time, so as an example of this, say two cars arrive at an intersection at the same place, they're at the center of the intersection at the same time, maybe they're going to collide with each other. We'll say they coincide, and if that happens at the same exact time, in other words, they're at the same place at the same time in one inertial reference frame, then they have to be at the same place and at the same time in any inertial reference frame, because if that weren't the case, there could be logical contradictions that would take place. So for example, if these two cars are in the same location, the center of the intersection, at the same time in one reference frame, perhaps they collide and the people inside the cars perish. It would be absurd for someone in another reference frame to say, well, they missed each other in my reference frame and the two people lived, because they could come back to Earth after traveling by really quickly in their reference frame. They could come back to Earth and we could say, those people are either alive or they're not. The cars are either mangled or they're not. So something happened there. And there would be a true logical contradiction if everyone didn't agree on what happened at that particular location at that particular time. So that's called the principle of invariance of coincidences. Principle of invariance of coincidences. If two, another way to think of it is, if when a rocket arrives on Mars, the local Mars clock read 12:16. Those are two descriptions of two events, right? The local Mars clock reading 12:16, that's something localized in space and localized in time by the reading of the clock. And the fact that a rocket arrived at the location at that particular time. That's another description of an event. So those two events coincide. If that happens in one reference frame, as seen by people on Earth, then that has to be true as seen by someone zooming by at close to the speed of light, and all their fellow scientists who are with them at different locations in space, but moving along with them at the same uniform rate. If they didn't agree, something tragic could happen and prevent it from one thing happening in one frame, and they'd be able to compare whether it actually happened or not. For example, when the clock reads 12:16, a laser beam, etches something on the side of the rocket. And if it's not there yet, well, it can't etch it on it and it misses the opportunity. So there would be some logical contradiction. So that's called the principle of invariance of coincidences. Here's another example. A beam of light, well, it's not, I want to think of a pulse of light. A pulse of light passes the 30-inch mark on this particular ruler. That's something that happens at a particular place. That's the 30-inch mark on the ruler at a particular time. There was only one time when that little pulse of light, here I've drawn it like a beam, but I'm imagining a pulse of light just passing by. If I see that happen in one reference frame, it's got to be the same thing happening in any other reference frame. And this may be related to something that was in Merman. I can't remember anymore. But why? Well, maybe when it goes by, it's such a strong pulse of laser light that it actually burns a little path across the ruler. So there's a little mark on the ruler, a little black mark of ash right by the 30-centimeter mark. And if we disagreed, maybe the other person in the different inertial reference frame said, no, it passed the 34-inch mark. We could all come back together later on and examine the ruler and see exactly where it burned the mark in there. So we can't disagree on where the meter stick's 30-inch mark was and where the pulse was at that particular time that we're talking about. The fact that those two events coincided in one reference frame, we're going to use that to our advantage, that they have to coincide in all other inertial reference frames. Any other questions on that? There were several reading response questions, and maybe I've got them at the end here. We're almost to the end of our time. Yes, so let's just finish up with some reading response questions. And again, it's just really a rush for me to get these up before class starts in the morning, since I can't get to campus too early. But let's see if I can remember what I was thinking when I put these on here. And I didn't quite move them down enough to get them from being obscured on there. Upon reading the example, knew something. Let me just take this off. Since I just put these up, I can't remember exactly what it says there. So we'll make it a little bit smaller. Upon reading the example, New York is about 1,000 miles away. I do not understand where he is coming from in that the statement is true or false with respect to one's location. However, as many others have pointed out, when Merman brought up the example 5 minutes after the game began, a touchdown was scored, I became a bit confused when he said that in that case, the location of the speaker did not matter, but rather how fast he is going past the stadium. So yes, in this case, the speed at which you're going past the stadium will affect, we'll find out, how much time difference there is between the event consisting of the game beginning and the event consisting of the touchdown being scored in the context of a particular, say, football game being played. In this case, unfortunately, I didn't read this text right before class, but New York is about 1,000 miles away. That is something that's being phrased from the point of view of a particular person. And of course, someone who lives in New York would never make that statement, or at least claim to be true about making that statement. If they live in New York would be about 0 miles away if you live in New York. So I think that's the point of the first statement. For the point of view of relativity, the second one is a more important and subtle and more something that's more difficult to come to grips with. Second statement here, I'm unsure if I'm understanding the concept correctly. Refer to, in the real world, B's clocks and meter sticks will, because they move with B, behave differently from A's equipment. Merman mentions that we have to be cautious when assuming that measurements agree. How is this idea incorporated into our predictions if our theoretical meter sticks and clocks all agree and are synced? So again, the problem comes from, we have a lot of intuition of how meter sticks and clocks behave when they're at rest with respect to us or moving only at slow speeds with respect to us. So when we say our meter sticks all agree, what we mean is if I take your meter stick and line it up against my meter stick and hold them at rest with respect to each other, they're going to be exactly the same length. Both ends will match up, right, when I measure their lengths. That doesn't tell me anything about if you run by with your meter stick and I, at some particular time on my clocks, I have whoever's next to the left end of your meter stick at that particular time and whatever observer is next to your right end of your meter stick at that time, record on my frame's meter stick where your meter stick ends were at that particular time, that they're going to agree and be, that the ends are going to line up. In other words, if I say, when the left end passes the left end of my meter stick, at that same time, from my point of view, where is the right end of your meter stick as measured on my meter stick? It might be at my 0.8 meter mark. We have nothing in our intuition that we've developed from watching things move around relative to us at 20 meters per second, 5 meters per second, that tells us how they'll behave when they're moving at close to 3 times 10 to the 8th meters per second. So when we say our clocks all agree and are synced, sure. When I have a bunch of clocks here, and I can certainly synchronize my clocks with ones in New York and even ones that are on Mars. The thing that we're calling into question is that I think all of those clocks are synchronized, and everybody in my inertial reference frame is going to agree. When someone moves by all of those clocks, And they make measurements. And when I say someone, I mean a group of scientists who are all moving uniformly together so they don't have to make distant measurements. They're going to see that at a particular time in their reference frame that my clocks all read different times. So they won't be synchronized anymore. So when one person says their clocks are all synchronized, another IRF is going to say, no, they're not. They read different times. One's ahead, one's behind, some are in the middle. They just vary, and we'll see exactly how they vary as we get into, oh, I think that's chapter 7. So it's coming down. I know that's frustrating because we can't understand everything right now, but it won't be too long. By the end of next week, we'll see all of these things. I'm wondering about the difference between actual time and our perception of time. Interesting question there. In other words, I'm assuming this means how a clock measures time and how I'm perceiving time elapsing. If you were moving more quickly than someone else, time would pass more slowly for you. But would you actually perceive that difference, or would it still feel like the same amount of time to both of you? So again, when you're moving relative to someone else, that someone else is going to assess that your clocks are running slowly. To you, because you're moving uniformly, you may as well be at rest. So you're not going to feel anything different. In other words, you're not going to feel like time is moving really slowly or something like that. There's no psychological effect. And you would look at your clocks and say, my clocks are behaving just as expected. They're not running any more quickly or slowly than usual. Both of the different points of view are going to say that their clocks are behaving the same way. So it's not going to feel any different. It will feel like the same amount of time elapses in between ticks of your clock. You're not going to feel that it's any different. The question comes, well, what happens if someone, as Jack did, travels away and then comes back and you compare two clocks? They're going to disagree in that case, and it's going to take some real hard thinking about why they disagree. There's an asymmetry there. You know, as long as two things are zooming past each other, there's sort of a symmetry between the 2 points of view. But if someone comes out and goes back, they break the symmetry. The 2 points of view aren't exactly the same, and we'll see exactly why that tells us that one of the clocks definitely reads a shorter amount of time and the other one a longer amount of time. Last one, it sort of makes sense now, but I still don't understand how light can behave like this and nothing else does. It's almost as if light is outside matter, a special kind of matter. What do you guys say about that? Jack? Yeah, I mean, physicists usually don't think of light as a kind of matter, but is there something special about light itself? Yeah. It has no mass, so that's really the only special thing about it, and you know, we'll find out that something about the association between having mass and not quite being able to be accelerated to the speed of light. But other than that, there's nothing special about light. And so everything that we can derive from the behavior of a pulse of light traveling exactly at the speed of light, if something travels very close to the speed of light, you're going to start to see the same effects for that physical body happening as you would for a pulse of light. So there's nothing special about light in that respect from other bits of matter. It's just that light can't help but travel really fast, and so these relativistic effects are always important for light. Whereas for other objects, they can travel really slowly with respect to me, and I may not notice anything that's in disagreement with my usual intuition. Okay, I feel like that was a difficult kind of presentation, and maybe it's because we're at such a difficult point in the course. But now, we've set up a bunch of conundrums that seem paradoxical, and we're actually going to start knocking them down one by one and seeing what has to be true. How meter sticks have to behave, how lengths have to behave, how clocks have to behave when compared between two inertial reference frames that are moving with respect to each other, and how exactly clocks that are synchronized, carefully synchronized in one inertial, exactly have to be asynchronous in another reference frame. And that's going to take some practice because we're used to assuming that, you know, of course, everybody's going to have synchronized clocks. Why wouldn't you? Well, the answer is you can't have synchronized clocks for everybody if they're all moving at fast speed with respect to each other. So that's coming in chapters 4 through 7. So hang on, and we'll start talking about the first effect, a rather mundane, it's sort of a non-effect tomorrow. The first real exciting one is going to be for Monday's class. Any comments before we break? All right, we'll be sure to have more worksheet stuff. I feel like I've spent way too much just me time talking today, and not enough time with us working and perhaps discussing, so we need to change that in the future. If anybody wants to stay and ask questions, hang out. That goes for you Zoom folks too. Otherwise, for the rest of you, I'll see you in Dr. Kadavid's class.
Hello, Dr. Kelly.
Hey, Mushiri, how are you?
Fine, how are you?
Good. Let me see if I can get my correct camera on so you'll be able to see me. Here. Hi.
Exactly. Hello.
It seems like your connection's working today. That's good.
Yeah, but it was going a bit off and on, but yeah, I got a lot of what was being covered. So I don't know why, but I don't seem to find the videos from Tuesday and Wednesday.
So one possibility could be that, unlike the Moodle site that we're using for Professor Kadavid's, every time you go to that site, pretty much you have to put in your credentials, log in, right? You put in your username and password. My website is a Google website, and it allows you to stay logged in for long periods of time. And unfortunately, what that means is if you open up the website today and then you come back on Monday, it will still be up. You don't have to log in again. But what it will display to you is what was shown at the last time you refreshed the website. So what I would recommend that you do is every time you visit my website, hit the refresh button on your browser, and it will reload it, and you'll see the most current version. Maybe that's the problem, because I have been trying to post the videos the afternoon afterwards. So the first, Monday, Tuesday, Wednesday, all have videos on there.
Okay. Okay, I'll do that immediately. Then I was reading Marmin's book, and I have a small question. I'm not sure if I understand this correctly. So there's a place he says, if you have the book, it's on page 11.
I
I'm not
do
sure if you
have it
have
with me, I think. Hold on, let me pull it out. Page 11.
Yes, at the statement that starts with "if the plane," exactly at the top, the first line.
Did you say it's the very first line on the page?
Yes, at the sentence starting with "if the plane."
If the plane were moving at 400 miles per hour, the man would be moving at 404 miles per hour past an observer on the ground, and at 804 miles per hour past an observer in a plane going 400 miles per hour in the opposite direction. Yes.
Now, I'm not really sure if I understand why the man is moving at 404 miles per hour.
Okay, well, so in order to understand that, we need to read what's at the bottom of the page before and make sure we understand the setup. And what I'm going to do is switch to a different video camera, so maybe we can draw something on the board.
Okay.
Let's see if I've got the right one here. Yes, this is showing the board. Do you have a question too?
Yes.
Okay, so let me just see if I can help Muchiri with this. And just be patient, and I'll be with you as soon as we're done here. Okay, so for example, if I remarked that a fellow passenger was walking toward the front of our plane at 4 miles per hour. Right, so let me get some chalk here. Here's the plane. Okay, so here's a person sitting at rest on the plane. And the plane here is moving how fast?
400.
400 miles per hour. So
Exactly.
we'll say this is going forward at 400 miles. We'll write it this way, miles per hour. And here's a passenger on the plane walking forward in the plane at 4 miles per hour. So the speed of this person is 4 miles per hour relative to the plane.
Yeah.
That means if we waited, for example, 1 hour, the front of the plane would have moved 400 miles to the right,
Yes.
plus this person, assuming they could keep going in the plane, of course the plane's not that long, they would have moved an additional the front of the plane would have moved 400 miles to the right, plus this person would have moved towards the front of the plane by an additional 4 miles. So they would have moved 404 miles relative to Earth in that hour of time. That's where the 404 comes from. Was that your question, or was it about the 804 as well?
No, no, I totally understand. Oh, wait. No, I understand about the one going in the opposite direction. Now, because when you explain this, I now can be able to relate this with the 804.
So your question is about the 804?
No, my question was about, I didn't understand how it was coming to 404. But now you've made it clear that we also
Okay.
counting, yeah. So
Good.
I think when I understand that, I can now apply the knowledge here to understand where 804 is coming from.
Okay, yeah, that's the idea. It's just adding together those two speeds.
Okay, sure, thank you. I think that is the only question.
So I asked you a question in email. Maybe you responded to this already about the reading responses.
Yeah.
Did you understand that?
Yeah. Like I said, I don't know. There was something with the website that I didn't understand, but now that I've explained it, now I understand it way better. So I'm going to do it.
I think I better
Right.
send an email to the entire class and tell them that every time they visit it, they should just refresh it, because it's nice that it allows you to stay logged in and you don't have to use your credentials every time. But the thing that's not nice is sometimes you might assume that nothing's been changed, whereas actually new material has appeared. So hopefully you see that. And if it's not working, if you don't see those videos listed, you should see the 4th video listed sometime this afternoon. You can watch them.
Okay, sure. Thank you.
All right, thanks. See you tomorrow.
Bye.
Or see you this afternoon, maybe, I guess.
Yes.
All right, bye. Okay.